Hope your day is going well. Mine is going beautifully. Delicious. Today we're going to go over length of curves. So before we did the shell method and the disk method for finding volumes. This time we're going to find the length of a curve. So along the same lines of thought, I'm going to focus less on memorizing and more on kind of understanding a concept or mnemonic to work your way through it. So for the disk method, we'd do something along the lines of pi r squared, and then do a small delta x, and then integrate from whatever your initial x is to your final x. And then we would rewrite r in terms of x. And would integrate with a bunch of disks. Well, we'd also did the shell method, where it would be 2 pi r, which would be the length of a circle, times the height of a cylinder, and then we'd give that cylinder a thickness of dx to create a volume. And then we would integrate from whatever the initial radius was to final radius. And then, of course, we'd make sure we wrote r in terms of x. Well, for lengths of curves, the concept we're going to go for here is draw a little axis, draw a happy little curve. I want something a little bit more curvy. There we go. It feels kind of harsh. I just killed that other curve. I feel kind of sad now. Oh well, I'm sure his memory will live on. I hope it wasn't a baby curve. Man. This is going to get me down. Okay. So the idea here is we can do a whole bunch of dx dys, and using the Pythagorean Theorem, we can then find the hypotenuse for each of these dx dys. So to find one of them, we'd do dx squared plus dy squared, square root the whole system, and then we'd integrate from, let's say we're going to integrate in the x direction. So we'd go from the first x, the x initial, to the final x, x final. Now your thought process is, all right, we've got these dx's and dy's, what do we do with that now? So what we're going to do is we're going to rewrite it as dx, it's dx quantity squared. I should have been more specific. I was not. So what we do is we factor out delta x squared. Still have our integrals. I'm going to leave off the limits of integration though for now. And then we can break this up into such. Squared, radical of integration, and then this portion right here, that becomes delta x, because delta x squared square rooted becomes delta x, and then we're left with a formula. This is more of a mnemonic than a proof, but it has a right general feel to it. I know, that is not a mathematical term at all. Right general feel to it. And I'll write this as f prime of x. So this is the formula we have then for the length of a curve, where we took the dy dx, which is a slope, small change in y, small change in x, and we added them together, square rooted them, Pythagorean Theorem, factored out at delta x, and then we have a integral here that we can solve. Ideally, we can solve. Someone can solve. We might not be able to solve it. Some of these get pretty tough. So I then just rewrote it as f prime of x, just a different way of writing it. And then we plug in whatever equation is, and we kind of see where it goes from there. One small thing to keep in mind is, even though I did this in terms of, I don't want to go back to orange. Too soon. Too soon, orange. Ooh, teal? Is this a teal? We could have done this the other way as well. So this could be, I'll go back to teal. I like deltas. I know they're not the right way of doing math. It's okay. Right way of math is getting the right answers. Nice thing about math is you need some certainty too that your answer is actually right. So we could have done it in terms of y as well. So sometimes when you have an equation, it might be easier to rearrange your equation so that it's in terms of y instead of x, and then go through the process. One thing for the AP exam is you're probably not going to have too much of that because you just don't have time. When you're talking about 2 to 3 minutes, maybe 4 minutes for a problem, then you're not going to have time to be like, well, I'll solve it this way. No, that seems difficult. I'll rearrange everything and solve it another way. You're not going to have time for that. So this is more for like a, if you're doing this for physics, or if you're doing this for like a college level calculus class. I know AP classes are supposed to be equivalent to college level, but they're not. You don't have as much time to take the AP exam as you do to do a whole bunch of homework in a college level class. So keep in mind there's a possibility you can rearrange your equation to do in terms of y instead of x. Okay, so now that we have this formula, let's do a few problems. Boom, boom, boom. All right, so we are given y equals x squared minus natural log of x over 4, and this is the curve, and we are going to solve this for 2 is less than or equal to x, less than or equal to 4. And your first thought is, well, let's draw a picture. It's a good thought, but I'm not even quite sure how to draw that, and we'll probably be fine. It doesn't look like there'd be anything where it would explode, because you might want to look for, like, you know, if you have x in the bottom and you have x minus 2 and then 2 to 2 and then you get asymptote. But it doesn't look like we're going to have anything like that here. So there's not even really any reason to plug this into your calculator to graph it. We're just going to go straight out with solving it. So let's see here. Start by writing out the equation. So the arc length will be 1 plus dy dx, which is f prime of x, squared, square rooted, integral dx. So this is going to be arc length, which we want to find. So let's find, first thing we should probably start with is we are going to want to find dy dx. Yep, I'm good with that. And we could think about, well, maybe we should rearrange this. Nah, it looks good enough. All right, so the nice thing about derivatives is you can pretty much always take the derivative. Might be a little bit cumbersome, but unlike integrals, you can always find a derivative. So I'm going to move a little slow here. Nope, f of x. F of x equals x squared over 2 minus natural log of x over 4. Okay, f prime of x. So now we're taking the derivative. Derivative of x squared is 2x. So we'll have 2x over 2 minus 1/4, because I'm just going to take the scalar, move it out. And then the derivative of natural log of x is 1 over x. The way I remember that is if you try and take the, I remember the integral of 1 over x. So 1 over x is x to the minus 1. If you try and take the integral of that, your thought process is, oh, I'll do the power rule. So you do x to the 0 divided by 0. Well, you can't divide by 0. The universe explodes, life ends, and it's best to be avoided. So that's how I know, okay, can't do the power rule. That must be the natural log 1. Okay, so now that we've got this, let's do the square of such. So f prime of x squared. So what I'm doing is I'm trying to find this term. So cancel out the 2's. So now we have x minus 1 over 4x. And I'll write it out again. X minus 1 over 4x. There we go. And then we'll use the FOIL method. First outside, inner, last. I just say the FOIL method and then I just do it. Multiply everything by everything else. X squared minus, okay. So we're going to have 2 times x over 4x. The 2 comes from 1, 2 because they're the same. And then we'll do plus 1 over 16. It's really a double negative. And we'll do 1 over x squared, which equals x squared. These cancel. Ugh. My penmanship is not as strong today as it normally is. Minus 1/2 plus 1 over 16x squared. Okay. So now that's what we're going to plug into our, I'm not going to say magical equation, but our equation. So let's see, up here. So we have integral 1 plus x squared minus 1/2 plus 1 over 16x squared. Square rooted, no, not quite. There we go. Dx. And you notice we have a green. Ooh, I do like green. I have a negative 1/2 here and a 1 there. You will see this pop up. These questions, to solve them, so one of your other first thoughts in life should be, oh, I'll plug that into my calculator, magic will happen, and it'll give me an answer, which is a good thought. Because most of these equations that you solve will be fairly contrived. And you will see this negative 1/2 added to 1 pop up a lot. You probably won't be solving that many of these equations, but like, again, if you're in a college level engineering calculus class and they really want to run you through the ringer, they'll give you a lot of these. So what happens then is we have x squared plus 1/2 plus 1 over 16x squared. And this just happens to be a perfect square. Well, a square. No square is perfect, man. I don't know if that was a 60s reference or a hippies reference. I don't know. Okay, so here we had 1 minus 4x. Well, when we add that, when we change that negative 1/2 to a plus 1/2, we get the same thing, except now we're going to change that to a plus instead of a minus. So we're going to have x plus 1 over 4x, quantity squared, square rooted, integral dx, which is integral x plus 1 over 4x dx. I know, normally you should show your work in a more concise manner. I did one of these and then came back up here and came back down. Wandering. These are the kind of problems too where you just get like a sheet of printer paper and you just put the problem at the top and you just use the whole front page of the paper. If you think back to like 5th grade or 6th grade and like, yeah, I can do 20 or 30 problems on one piece of paper. You get up to this level, it's like, yep, 1 problem per page. Sad. Sad indeed. So we have x squared plus, was it 1/4? Natural log of x. X squared over 2. Natural log plus 1/4 natural log of x. And we'll evaluate it from, what was it, 2 to 4? 2 to 4. Okay? Maybe over here. And I'm going to switch it up to blue because I'm pretty sure we're going into the home stretch now. So we have 4 squared over 2 plus 1/4 natural log, and I'm going to write this as 2 squared minus, make this whole thing a quantity, move my image up slightly. Now I'm going to have to start writing smaller. 2 squared over 2 plus 1/4 natural log of 2. There we go. Get some purple. So this 2 can go over here. This can be 16, which makes this whole thing 8. This is, that cancels, so we get 4 divided by 2, which is 2. And then we have, this is 1/2. Nope, we'll keep that one the way it is. I think I missed a lot of things I wanted. 4 divided by 2 will be 2. That'll be 2/4 and 1/4. So we have 8 minus 2, which is 6, plus 1/4 natural log of 2. There we go. And then we don't have to have the plus c because this is a definite integral. Only when you have indefinite integrals do you need that plus constant. With definite integrals, with an actual beginning and actual end, the beginning and end will both have the same constant, and so when you subtract one from the other, that constant will disappear. So this will be then the answer, 6 plus 1/4 natural log of 2. Let's see. Oh man. Up and then over. Okay. So that's the general concept for how you do one. Let's try one more. Let's erase this. Oh, I don't like how I wrote that, the formula that time. Okay. The same concept. We look at it. We're like, okay, find the arc length of said problem. Delicious. Thank you, Crystal Light. It's one of those fancy Crystal Lights with caffeine in it. So delicious. And energizing. I think the phrase they use in the packaging is with energy. I'm like, it's just caffeine. Which is still magical. Okay, focus. So arc length. And we'll do 1 plus f prime of x. Quantity squared, radicalized, dx. Okay? And so, let's see here. F. I panicked halfway through that. Gotta commit. So 4 minus x squared. Square rooted. And the first thought here then is first thought is like, well, maybe I can rearrange this to be in terms of y instead of x. Nope. And then you keep trying to think just with the goal of trying to avoid a trig substitution. Because avoiding trig substitutions in life is a pretty good policy. Gee willikers, I hate trig substitutions. Bane of my existence. But We all have our burdens to carry in life. Life isn't easy for anyone. All right, so here's the derivative. Is that true? That seems reasonably true. Yeah, I'm good with that. So then f prime of x squared. Let's see if I actually did that right. Then, oh, it's supposed to be a negative. Almost got me. Almost got me. But then we can, okay. So then, squaring that, the 1/2 and the 2 will cancel out. So I think it'll be negative x squared. Alright. First I'll write it out, then I'll square it. So we'll have negative x on top, and then we'll have 4 minus x squared to the 1/2 on the bottom. And then this whole thing should be squared. And that gives us an x squared on top. I'm worried about losing information there. Hopefully it won't come back to bite us. Maybe it will. Maybe it will. And then we're left with four minus x squared on the bottom. Yeah, which seems reasonable. Okay, I'm good with this. And then we need to add 1 to this. So going back up here then to our formula, draw an arrow. So we want the integral, trying to get everything in the board. There we go. Zoom out slightly. Zoom out. Okay, so we have 1 plus x squared over 4 minus x squared square rooted dx. Okay. Fear not all is hopeless. I'm going to rewrite this 1 in terms of 4 minus x squared over 4 minus x squared. Because the top and the bottom are the same, then they'll just equal 1. Unless that same number is 0, in which case you're dividing by 0 and the universe ends. You should avoid that one. You stay away from that dividing by 0. Nope, that looks like a 9. There we go. And then I'll put the square root on the top and the bottom, just separate it out. Do a dx here. Change color for contrast. Ooh, purple. Cancel, cancel. And then we get square root of 4, which is 2, which I'm going to move to the outside. There we go. And I'm celebrating, but part of me is also like, that's definitely a trig substitution now. Definitely. No way to avoid this. Okay, so remember back to trig substitutions. So you do x equals, and if the sign, the negative sign, is on the x, then you do x equals sine of whatever. If the negative sign is on the constant, then you use secant, x equals secant, or a secant or whatever. And if you add the two together, then you're going to use x equals tangent. So for this one, we're going to say x equals 2 sine of theta. Now we also need to find dx, which is 2 cosine of theta. Okay. Clean up some of my workspace. There we go. Man, see how I got so far diverted? Outrageous. Okay, so we got 4x and a number there. Do we plug stuff in? I think I just plug things in now. Yeah, that will be the best course of action. So we'll have, on the top we'll have dx, which will be 2 cosine theta, over 4 minus 4 sine squared of theta. Had the parentheses up there, but not down there. There should also be a d theta over there. You can think of it as the chain rule. Square rooted. Rewrite things slightly. And we have, let's say 4 on the outside, just factoring out the 2. Leave out the cosine theta. And then we're going to have square root of 4 times square root of 1 minus sine squared. I'm just going to leave off the theta this time. Equals, yes. So this becomes a 2. So we have 2 integral cosine theta. 1 minus sine squared is, so we have sine squared plus cosine squared equals 1. So 1 minus sine squared equals cosine squared, which when square rooted becomes cosine. I feel so proud of myself. Very proud. Quite accomplished. Oh, cancel. D theta. So I should probably find the limits of integration. I'm not quite sure how I would convert this back into x. So I'm going to try and find out what the limits of integration would be here. So I'm going to call this, we're going to go from theta 1 to theta 2. So rewrite this real quick. Come back over here. So our arc length will be 2 times theta from theta 1 to theta 2, where theta 2 equals, I'll make an arrow. So our big X, I'm going to come over, no, this is the problem of having all my work spread out like this. Unacceptable. So 2 and negative 2. So 2 equals 2 sine theta. Therefore 1 equals sine of theta. Therefore theta equals pi over 2. Alright, so theta 1 will be, it was negative 2, would equal 2 sine theta. Therefore theta will be negative pi over 2. I think we can do 3 pi over 2 as well. But since it goes from negative to positive, I have a feeling it would work out better if we do pi over 2 and negative pi over 2. So we do 2 theta from negative pi over 2 to pi over 2, which would give us 2 times the quantity pi over 2 minus negative pi over 2, which will give us pi, and our final result will be 2 pi. Okay. So I know your eyes probably glazed over for some of that. It was, wow, look at that. Look at that adventure. And I even erased some of it. So to backtrack, the concept here is, all right, so find the arc length of this equation. And so we start by writing up the formula, 1 plus f prime of x quantity squared, and then we take the square root of that, and then integrate with respect to dx if we're using f prime of x. If we're using dx dy, then we'll integrate with respect to dy, but probably dx. And then we find f prime of x, we square f prime of x, we plug it into 1, we shake up that equation, hopefully to make something that is useful. In this case we did by combining the 1 using the denominator. We then found out we had to do a trig substitution. We cried a little bit, and then once our tears dried, we got to work. And we found out that everything kind of canceled pretty well. And we were left with a relatively simple 2 pi. And your first thought is, gee willikers, how could I possibly be tested on something like this for the AP test? Which is a good wondering. If you're contemplating, well, should I take the AP test or should I just take calculus in college? You know, I'm in high school right now. I'd rather be lazy and then, you know, do a little bit of work, get an easy grade when I get to college. I would recommend against such. Yeah, when you get college calculus classes, they are brutal. They're not, the concepts aren't any different and they're not more difficult, but you just so much, you get problems like this. Let's look at it, what we'd see for like an AP exam. So this would be the sort of question you might find on an AP exam relating to arc length. So, which of the following integrals gives the length of the curve y equals ln of x from x equals 1 to x equals 2? Oh, okay. So, do the same thing. Write out the equation. Ooh, wonder how far I can zoom in. Ooh, maybe too much. All right. So it would be arc length equals integral 1 plus f prime of x square rooted dx. F prime of x equals derivative of natural log of x. F prime of x squared equals 1 over x squared. Therefore, the arc length will be 1 plus 1 over x squared square rooted dx. And then I'm like, I'm not quite sure how to solve that. And I think about it, I'm like, oh, that's all they wanted, was right there. So I was able to solve that problem in, well, okay, I'll put down the limits of integration in like less than a minute, 30 seconds, where you're looking at like 5 to 10 minutes if you're proficient at like not a real problem per se, but the kind of problem that you would find in a college level calculus course. So the nice thing about the AP test is they just don't have time to test your knowledge that way. They could ask you something like this on like a free response, but there are better things for the AP test to ask you on, which will do a better example of testing your knowledge, where when you're talking about a multiple choice question, you really don't have time to get into all the weeds that is consistent with an arc length problem. So you know the formula, you have kind of a mnemonic of how to kind of derive the formula using the Pythagorean Theorem and factoring out a delta x. And after that, that's pretty much all the studying you need to know for this, which is really pretty nice. So I should probably actually finish this problem out. So 1 to 2, 1 to 2. Oh, they're all 1 to 2. Okay. 1 over x squared. So we got this one. That one doesn't have the radical. I don't know why they have it either. This, they're just hoping you don't know what you're doing. And so that question right there. So we have know the formula, plug the formula in, done. So that is the idea with arc length. And it's good to know, but it's just another technique to help you get through line arc lengths. So we covered volumes, shell and disk method. Now we did arc length. And now another strategy we're going to talk about, not so much with integration per se, yeah, sort of, is partial fractions. So you've probably maybe already seen partial fractions. It takes like 10th grade level knowledge of how to, maybe 9th, maybe earlier. It's not a high level concept, but it's an interesting trick that it's an interesting method that you wouldn't normally stumble upon, and you should practice at least a few times to kind of get an idea of where it's coming from. So that's all we have for arc length, and I will see you